Afternoon, everybody. Good to be part of the 3CDT. I think it's a really good idea, and I'm glad we're being able to do this at last. Certainly something that's been talked about for over 12 months now, but anyway, it's good to be here, so thank you. So my name's, just to do a quick introduction, so my name's Nick Kitchen. I'm CEO of a company called Cumulus Energy Storage, and we are essentially specialized in our own longer duration energy storage system. And just to give you a bit of background, we're currently working, and this is part of this talk, is to help from a dissemination point of view for the project that's currently funded by BEIS. So we are currently part of a 4 consortium member project. It's a feasibility study. It's designed to help make sure that we've got ourselves lined up for putting some longer duration energy storage at containerized scale in a phase 2 project, which follows on. It's a £9.45 million project, and the aim is to put our containerized storage onto this heavily constrained and therefore curtailed wind farm in order to improve the overall profits for that wind farm, but principally to help drive down the decarbonisation of the electricity grid. So there are a number of different motivations behind this particular project. The partners on the project are essentially, obviously, Cumulus Energy Storage, providing the battery technology. There's the University of Southampton. Andy, of course, is working very closely with us. And there's some quite a lot of technical development work that's currently being undertaken by the university right now, and that's informing our feasibility study report, which has got to go in May. And then the phase 2 program is due to start in September, October time, hopefully, phase dependent. The other party in the consortium is Energy Systems Catapult, and that's great because they're going to take our site level experience and modeling and all the rest of it and take that out and translate that into system level effects. So it's important that we've got not just a battery system on site, but hopefully eventually we'll be able to follow on with a hydrogen electrolyzer on the same site and therefore have multi-vector forms of energy storage as an end result of this project that we're doing the feasibility study for right now. Obviously, we need a wind farm owner to allow us to put the energy storage onto their wind farm. So there is a wind farm owner that we are currently in discussions with. We're currently onboarding that wind farm owner. I'm not at liberty to say who that wind farm owner is yet, but suffice it to say that on my list of 29 heavily curtailed wind farms that I'll walk you through later on, they are one of those wind farms on that map. So hopefully that sets the scene. So Cumulus Energy Storage, I've said we've got longer duration energy storage. It's our own technology. It's rechargeable copper zinc. So if you go back some 200 years to Volta, he invented the single-use copper zinc battery that was used in the telegraph industry for many, many years. The novel bit that we've done, and we now have patent granted across 16 countries in the world, which is about 2/3 of the world's total electricity consumption. So the bit that we've done is we put a membrane in between the copper and the zinc electrodes, and that's the bit that's facilitated the whole technology to become rechargeable and therefore applicable to the energy storage industry. So I've been working on this since 2012, and was, if you like, inspired, if I can use that term, to look at this because I was listening to the politicians talking at basically an offshore wind conference on the Humber in March 2012. They were talking about the same amount of steel as currently is used in the car industry, 50 billion going into it, 7,000 wind turbines, big numbers. And I was doing some consultancy work, which was completely unscalable at the time. And I'd been looking around for an industry for quite a long period of time that is scalable. And this seemed to be a good opportunity. So shortly after that, I went across to California. I bumped into another friend of mine from London Business School where we did our MBAs together. And we had Friday night conversations about, can we work together? And if so, what can we do? And we very quickly honed in on the energy storage side of things. Because of Darren's background and his CTO's background, we were able to challenge his then CTO to say, okay, which technology should we use for energy storage if we want to make big batteries and help integrate renewables? He came back with the copper zinc, and the rest, as they say, is history. So that's a little bit of background about where we've come from so far. So As you know, Scotland is blessed with about 25% of the total European wind resource. And unlike England, government policy is very much in favour of having onshore wind turbines as well as offshore wind turbines in Scotland. So there is several different projections and predictions in terms of how much onshore wind, offshore wind, and therefore energy storage is going to take place between now and 2050. And those numbers on the right-hand side are very, very significant. And just to put it in perspective, we've got about 10 gigawatts at the moment of offshore wind, and the government is saying 40 gigawatts by 2030. But actually in the modelling that BEIS has done, we're talking about up to 125. It's a really large increase. And the issue I'm going to talk about now is how on earth you get that little lot into and through and across the various networks across England and across GB. So I first became aware of the issue of constraints some time ago. It was becoming fairly obvious that the cost of those constraints was going up and going up very quickly. 2000 was a watershed, not just because of COVID, because it also showed the impact of, and gave us, if you like, a vision as to what was going to happen in about 4 or 5 years' time with regard to high percentage of renewables in the mix. What does that actually mean? Well, that is what that actually means. It's a very much increased constraint cost. And most of these constraint costs are driven by the boundary, literally the electricity network boundary at the Scotland-England border. It's called B6. And because the capacity of that boundary is limited, it means that sometimes, in fact, quite often, the wind farms, when it's windy in Scotland, are told to curtail. They are constrained by this B6 boundary. And the perverse result of that is you have to then start switching on high carbon electricity generation south of the border. So it's a double whammy. You're turning off the low carbon and you're adding on the high carbon. So what I wanted to do is try and find out whereabouts in the GB were these wind farms that were getting heavily constrained and therefore curtailed. And yes, I understand that people offline can't see the pointer here, so I won't use the pointer, but essentially there are two groups of wind farms. First wind farm is immediately north of this. There's the Scotland-England border here, and there's another group of wind farms around Loch Ness. Those 29 wind farms account for 80% of the total constraint cost in 2020. So that's where the issue is. Also had a look at the amount of curtailment, in which country, whereabouts, onshore, offshore, etc. And it's pretty obvious, when you look at those numbers, that the curtailment is basically in Scotland. It's about onshore wind, and as a percentage of what was generated in that year, that curtailment cost is a very large percentage, 17.6%. So the cumulative solution, why is this relevant to constrained wind? Well, firstly, we're talking here about a longer duration energy storage system. We're talking about 4 to 12 hours charge and discharge times, which is really, really helpful when you want to actually tackle some of the curtailment issue. We're also talking about a very green solution. We've got abundant materials, abundant metals that are used. So not just the zinc and the copper, but also aluminium and stainless steel are the fundamental materials in the electrodes. And then even our electrolyte, which is a liquid, is biodegradable. So it is a very clean green solution, and it's very recyclable. So 99.5% recyclable. Contrast that with the lithium solution at the high power, short duration part of the market, recycling issues at the end of life. Ours is in the high energy, longer duration part of the market. Very different set of services, very different role in the overall market. And because of the structure, and because we can maintain our system, and because it's very easy at the end of life to recycle, then we can end up saving ourselves roughly 60,000 kilos of CO2 for every megawatt hour per year, compared to lithium iron phosphate. So one of the other beauties about it having not just a longer duration energy storage system on a constrained wind farm, but if you then combine that and you put a battery behind the meter, so you can do a private wire system and effectively have green electricity supplied into the hydrogen electrolyzer, you can do two things. Firstly, obviously, it's green electricity because it's behind the meter. And secondly, you can also reduce the cost of that electricity very, very significantly. So just to give you 2020 price example, down from about £50 a megawatt hour down to more like £9.85 per megawatt hour, about a £40 reduction. And given that 70% of the cost of hydrogen comes from the cost of the electricity that goes into it, that's where you can end up with this £2 a kilo reduction in cost. And that means we can make green hydrogen at the same or lower cost than blue hydrogen. And that means we can then start to influence and help decarbonize the steel industry, cement industry, transport, etc. So this is a multifunctional, multi-vector project as it's going to pan out. So nearly all the wind farms that I'm talking about are the transmission connected. They've all got ROCs. So one of the assumptions that I made in the modelling for this was that the ROCs payments will be unaffected, and we made sure that the metering arrangement was also going to facilitate that. So Ofgem have put out a number of suggestions, recommendations, if you like. If providing you use these kinds of metering arrangements, you will still be able to claim ROCs for the wind farm generation, even if it's then going into the storage and out from the storage into the network at some later point. So I'm going to talk to you about Kilgallock. Kilgallock is one of those 29 wind farms. It's in South Ayrshire, so it's on the west coast, or close to the west coast of Scotland. It's again north of the Scotland-England boundary, about B6 I mentioned before. It's one of the largest wind farms in Scotland, 228 megawatts. Those 57% curtailment losses, you'll see some of the graphs in a minute that demonstrate why that's the case. But that 57% is based on the amount of curtailment divided by the amount of generation that took place that year. So it's a different form of calculation compared to how the wind farm owners do that. So in January 2020, those sort of green-brown lines are the generation that took place in each half-hour period. The blue-grey bit is the amount of curtailment that took place. In other words, how many megawatt hours were lost because the wind farm was constrained on each of those days. So you can see that the constraint is a very significant part in relation to the overall generation. I also took on board the number of megawatt hours generated, the amount of constraint in each settlement period, and then the market price for each settlement period to inform the modelling that we did to see, is there a business case for storage at Kilgallock? If you go down and look at how much of the, how many days a year are you able to generate? That's the big blue bit, roughly 250 days, 40 days or thereabouts with no wind at all, and the rest of the time is based on some form of constraint in the system. So from an energy storage point of view, obviously it's quite helpful to know what scale storage do we need to have? Is the storage actually needed? How long does that storage need to act for? And I was really, really surprised to see that there were nearly 200 individual events that were curtailments at Kilgallock in 2020. And if I plotted all those on this top right-hand graph, the bottom right-hand graph is essentially an exploded diagram of the first 6 hours of the top graph, just to put that in context with you. Hopefully, that there's a fairly straight line across the top of those dots in the top graph. And what that suggests is that if you're going to maximize the amount of curtailment reduction, you need to have an energy storage system that's the same power as the wind farm. So in our case, it would be a 228 megawatt 4-hour storage, so 912 megawatt hours system. So you're talking about significant scale storage. But when you put that kind of storage in place, and particularly if you then back that up with a second battery that's behind the meter, that's then feeding green electricity into a hydrogen electrolyzer, you can reduce that curtailment with the first battery by 28%. You can reduce the curtailment by the second battery with a further 17%. So that's 45% curtailment straight away. And then there's a further 20% curtailment reduction that's available through use of the electrolyzer, where that electrolyzer is roughly 1/3 of the power of the wind farm. So those are the kinds of mechanics and calculations that are in there behind the system. And I've used 3 revenue streams. One is when the wind farm is constrained, therefore it's not allowed to export any electricity into the grid. That means you've effectively got free electricity that's going into your energy storage system. And then there's a selling price for that once the constraint has disappeared. So there's a decent profit margin associated with that. The second one is to give generation support. So this is when the market price is low. So it makes more sense to put that electricity into the energy storage and then export later. And thirdly, when the market price is low, to import from the grid, and then when the market price goes up again, obviously then export. So there are a number of different arbitrage opportunities that drop out from this setup. I've added in just one ancillary service at the moment. We could add in several more, but the reactive power is one of those, and then putting the capacity market as another one. So we've assumed that the first battery, I don't want to go into too much detail here, but the first battery is designed to be empty at the point where the constraint starts. So I'm assuming that there's some sort of advanced notice. So the first 4 hours is there to charge the system. And then the rest of the modeling goes on to make sure that you maximize the amount of revenue coming in for the wind farm. When you look at the 2 different size batteries, so the top graph is where you've got a 1 megawatt, 4 megawatt hour system. So really, really small compared to the size of the wind farm. Most of the cycles that battery goes through are either the constraint-led cycles or in other words, when it's curtailed, or the generation-led cycles. On average, that works out to be about 1.3 cycles per day, 100% depth of discharge. So it's not an unreasonable thing to have modeled. And the bottom graph is a much bigger system, and that you can see a lot more gray lines on that, and that's indicating that there's a lot more import and export from and to the grid at times when you've got that arbitrage opportunity. So the price points we're talking about here, and bear in mind these are 2020 price points, but we're completely out now for 2021/2022, obviously. But nonetheless, free electricity going in for the constraint, £39 a megawatt hour for export purposes, and then both generation and import is optimized by having essentially £33 or less import price and a £40 or more export price. You might say that difference isn't great, but actually there's an awful lot of negative prices when you're looking at the import side of things, and very high export prices at other times for that arbitrage. So if you just take the arbitrage opportunity and don't take into account the ancillary services, for a larger scale system, you're talking about an IR that's around 11%. So it's double digit. It's not terribly exciting, but it's okay. When you start adding in some of the ancillary services as well, then you start talking about more like 15% IRR. And if we then added in some more ancillary services, we should get between 15 and 20% IRR. And of those sorts of IRRs, you're going to get people that are really excited about this whole thing. But as I say, the main driver for us is not just to have the business model that says, yes, it makes sense to put energy storage at a constrained wind farm, but also then there's the secondary benefit, which is the decarbonisation of the grid. So the slightly perverse scenario, I don't know whether you know this already, but there's a slightly perverse scenario out there. So if the wind farm owners are told to turn off their wind farms, they actually get paid more than they do if they generate low carbon electricity. So when you're trying to decarbonize, how does that work and why is that structured like it is? So there's a potential policy change from Ofgem that we're looking for, whereby instead of paying the wind farms constraint payments, which is how they get paid more than they do by when they're switched off, instead of paying them constraint payments, you pay them instead to generate hydrogen. So make it into a win-win for everybody. And then replace the constraint payments, well, not constraint payments, replace some of the incentive for the transport side of things, add on to that some other incentive to do the same thing in terms of decarbonising the industry, whether that's cement or steel, etc. And I think that's all I wanted to say. So there you go.
Hi, thank you very much. That was really, really exciting. My question is, do you have plans to expand this to other sorts of renewable energy? I mean, so we hear, a lot of us here at the back, from the solar CDT, and similar problems are experienced there. You know, when it's high summer, the sun's beating down, a lot of the solar farms have to turn off because there's just no demand.
Yep.
But I feel like this is completely generalizable to essentially any scenario like that. So I was wondering if you had any plans.
Have you got a couple of hours to talk about it? There's so many options.
Yeah, I would love to. Yeah, that sounds really great.
Just to summarize 2 hours in about 35 seconds then. So yes, obviously this case study is about wind, equally applicable to solar, equally and even more applicable to offshore wind, at which point you start talking about gigawatt hour scale systems. So part of our plan is already contemplating a set of offshore wind farms and where they come in, and they're constrained substation right now. And then how that links in with a former power station and that grid connection at 2 gigawatts, and how we could effectively have a 8 gigawatt hour energy storage system. So in terms of scalability, the opportunities are just ginormous, and that's just in Scotland. Okay, then you start talking about other parts of the world, and so it multiplies out. Other applications include things like diesel engine genset replacement. So X 100 million people in India, for example, same applies in China. Then you start talking about data centers. From a site energy management point of view, you need about that 4-hour time frame. So this is not the UPS scenario, but it's for the site energy management perspective. Ireland, full of different data centers, amazing market, ideally suited to us for the longer duration stuff. Even the DS3, it's all set up for longer duration energy storage in Ireland. So those are just a few examples, and I can keep going on if you like, but yeah.
Thank you very much.
In terms of market opportunity, unlimited. We just have to get the technology out there, proven, demonstrated, hence the work with the university at the moment. So
excellent. Thank you very much.
Yes, you could have predicted that I'd have a lot of questions, but
yes, quite right.
So first of all, you were talking about was it about 900 megawatt hour? Did you mention
912? Yeah.
Yeah. What kind of size system would that be? As physical dimensions.
Okay, so a 70 megawatt hour system. So call that a tenth of the size, round numbers. Is about 3,600 square meters. So 36,000 square meters or 360,000 square feet in round numbers.
Right. Okay. So what I'm driving at with that is this sort of limited in the aspect of you need a lot of space to be installing these systems, which is an excellent selling point for offshore and Scotland, where there is a lot of open space. But when it's a more built up area, you can't.
Yeah. So obviously lithium ion. The energy density of lithium ion isn't actually that great. At a cell level, yes, clearly it is. But by the time you have to have the separation of various stacks from a fire safety point of view, your energy density isn't actually that great from a footprint point of view. So yes, you wouldn't want to put our system into a Tesla, for example, because it wouldn't go anywhere. You wouldn't want to put our system into the basement in a city of London. But our markets and really the market requirements and market needs are all looking at things like renewables. Space is really not an issue. It's just not a metric that people ask me about. They want to know about price. They want to know about delivery. They want to know about recyclability. And those are the sorts of questions that come out, not what is your energy density or power. It's just not relevant.
And the last one, promise, for now anyway, is how scalable in the other direction is it? So
in what sense? When you say the other direction, how small?
Yeah, how small can it feasibly be marketed at?
Okay, so our base system is 250 kilowatts, 1 megawatt hour. So that's a 45-foot high cube container, just to give you a feel for the DC side of it. And then next to that, you'd have a 20-foot container with the bi-direction inverter in it.
Cool, thank you.
Software.
Perfect.
Thanks a lot. Yeah, really interesting stuff. Just to push a little bit harder on a couple of those technicalities. So I work in the marine sector, and sooner or later, someone
You work
in the marine sector,
okay.
and sooner or later, someone always decides that it's a good idea to try and put technologies that were clearly designed for stationary applications and suggest that marine would be a suitable endpoint for them as well.
From a
So
tidal point of view?
Sorry?
From a tidal point of view?
No, on boats. Now,
Oh,
I'm assuming
no,
you.
yeah, okay.
But just out of interest, then could I push you to a volumetric energy density and a gravimetric energy density for the system?
You can try. I don't have answers for you.
Okay,
It's just not relevant metric for us.
Yep.
But if you're also asking the question, would we put our system onto a ship? The answer is no. And the reason the answer is no is because our electrolyte is liquid. So you wouldn't want to have that sloshing around inside the ship. Basically.
Fantastic. And about the cycle life of the system.
Okay, so one of the beauties of our system is that the one wear component is the membrane, and that we can replace a low-cost component. We can replace that. Eventually, we'll get to about 7 years on one cycle a day. So if you then do 3 membrane replacements, which doesn't cost very much at all, then that can take you out to about 10,000 cycles or 30-year life. So it's a totally different. It's more of an infrastructure asset than it is a battery, if you can think of it in that terms.
Fantastic. Thank you very much.
Just wondering if you've costed this against reinforcement. So rather than curtailing the wind farm, if you put in more network capacity, how your battery system.
It's a very good question, Andy. Yeah. So as you know, National Grid put out a number of future energy scenarios. The latest one came out 2020, late 2021, I think it was. Anyway, they've got four scenarios in that. They take essentially one of those scenarios for least regret decision making in their network operation, in what they call the NOAA, those different assessments that they're making. Basically, the end result of that is that they've got a £16 billion budget today to spend over the next 10 years on network reinforcement. Okay, now I've got people like Imperial College, I've got Aurora, I've got Bayes reports. All of those say if you put a sensible amount of energy storage into the system, and indeed in the future energy scenarios, there is a very significant amount of additional storage, regardless of which scenario you talk about. So that is going up. But as a base case, there is an opportunity for us to save significant sums of money. And then I say that because the estimates are quite different according to whose report you read. But basically, every single one of those people say there is some significant cost saving from a network upgrade point of view by putting the longer duration energy storage in the system. So the thing that's been missing historically is the business model for the longer duration energy storage. Most of the short duration storage has been based on, as I'm sure will be talked about later on this afternoon, most of the short-term lithium storage standalone systems is based on short-term contracts, but they are contracts nonetheless in the ancillary services market. This is about looking at the benefits for the system as a whole by taking longer duration storage and helping to debottleneck and decarbonize the grid as a whole. So I think that's partly answered your question. I couldn't actually get a direct correlation. I did try. Haven't managed to get a direct correlation yet between the uplift in the renewables and the cost savings by putting the storage in. I couldn't get that, but there are savings. Okay. No? All right then. You've got one. Good stuff.
Have you compared the price?
Yep. So if I talk about the flow batteries, just to give you one example, vanadium redox. So here's my hypothesis on flow batteries. They'll have niche market opportunities. I don't see them being mainstream. And the reason I say that is because the vanadium redox has got a very, very, very expensive electrolyte. It's got marginal cost benefits through scaling and increasing the duration, so that's fine. But it's still fundamentally a very expensive system, and there are other issues with it in terms of self-discharge, etc. And then the zinc bromine is the other one. That's the main one. Has got various environmental issues associated with it. So, so that's my take on that. Gravity, yes, definitely got its place. It's just a different part of the overall spectrum, but you'd have to have, you know, either pre-drilled mine holes or you'd have to drill your own mine holes. So, yes, it will be there. It will have a significant market share, but it's just another one of the technologies, and we need every one of them. So. Oh. Should we expect similar cost? Because of the base metals that we're using, the active metals that we're using in our system, today we'd be more expensive than zinc bromine, but very, very quickly we'll drop down well underneath not just zinc bromine, but we'll drop down below lithium ion as well. So at a cell level, by the time we get out to just a few gigawatt hours of total cumulative production, we'll be well under the $100 at cell level. And given what's going on with lithium prices, lithium carbonate prices, given what's going on with nickel, cobalt, any other metal you can reasonably think of at the moment, yeah, not a problem. Back again, back for more. Okay.
It's a compliment. It means it's interesting.
So I didn't mean to hijack the whole of the afternoon.
Going back to the degradation element of it,
Yep.
and you mentioned the membrane being easily replaceable.
Yes.
For a low cost.
Yes.
What sort of percentage of capex would it be to replace that membrane? And is it something that you mentioned about potentially with one cycle a day, you'd replace it 3 times? With more cycles a day, could you replace it more times?
Yes.
Yeah. So the other elements aren't degrading, as the membrane is the pinch point, basically, is what I'm trying to say.
Essentially, providing the revenue streams make sense to keep doing more cycling. If you do more frequent cycling, obviously you're going to be wearing out the membrane more quickly.
Yeah.
But providing the economics make sense, why not?
Yeah. And is it a fairly straightforward cycle degradation link? So if you cycle it once, you're at a certain power, you're going to have a similar level of degradation of cycling it at a different power. We're actually going through that exercise at the moment. We're actually finding out the parameters of the battery system. It's part of the work that the university is doing to work out and find out how far can we push various parts of the performance curve. And answered your question about the membrane cost, but it's a very small percentage of the capex. Yeah.
Okay, I think we're going to have to stop the questions there. We can
Good,
take it up
fine,
in the kitchen.
thank
But
you.
thank you very much for your talk. Thank you.
Our next speaker is Flora, and she'll be talking about quite a similar topic: how we optimize the economics of onshore wind using energy storage.
Hi everyone. As you can probably see from the title of my presentation, this is going to be on a very similar topic to the talk that we just heard from Nick. So thank you very much, Nick. You've actually made my job much easier by already convincing the audience that this is a really important topic that we should be considering. So yeah, in my talk, I'm going to be addressing the question, can we optimize the economics of onshore wind using energy storage? And I'm going to start by outlining the background and the aims of this study. Then I'm going to present my methodology and my results and finish with a bit of discussion of some future work. We all know that climate change is bad. And one of the ways that we can combat climate change is by employing renewables, such as solar and wind. But what do we do when the sun doesn't shine and the wind doesn't blow? So that's where energy storage comes in. So energy storage is great because it can bridge the gap between electricity generation and electricity usage, which is fantastic. However, it is very expensive. So in order to encourage more people to invest in energy storage, we need to find ways that we can use it in order to generate revenue and therefore encourage investments in this technology. There's been quite a lot of literature looking at optimizing the economics of wind storage systems. So I'm just showing some of the more recent ones here. There's been literature in optimizing wind battery systems and wind hydrogen systems, but there's actually not been that many that consider both battery and hydrogen together, and even fewer that also consider curtailment. And as we've just heard, curtailment is a very important issue. And as we get more and more renewables, then we expect that we're going to get more and more wind and solar being curtailed. So it's something that we do need to consider. That's where this study comes in. So in this study, we've created an optimization model that maximizes the economics of a wind storage system with battery storage, hydrogen electrolysis, considering wind curtailment, and doing it all from an investor point of view. So the aims of this study are to realistically model onshore wind co-located with energy storage and to optimize the scheduling of that storage to maximize its economics, and also to examine how the storage can make use of the curtailed wind that might otherwise be wasted. So firstly, I needed to model the onshore wind. Unfortunately, there's not a whole load of data available on wind farm generation. Actually, you often have to pay to access this data, which is not what I wanted to do. I wanted to use a method that could be easily replicated using openly available data. So what I did was I combined some weather data from the Met Office and some wind farm data from the Renewable Planning Database. So I'm showing that here, again, in Northern Scotland. So I'm showing with these circles the onshore wind that is operational, planning permission granted and under construction, and the size of those onshore wind sites. And the black crosses represent weather stations that have a whole load of data on the weather, including hourly wind speed and direction. So when choosing a site for my case study, I wanted to choose an onshore wind farm that had a really good overlap with one of these weather stations, so that I could make the assumption that the wind speed measured at that station is going to be very similar to the wind speed at the wind farm. So I chose this site here, and it's also kind of a typical size for a onshore wind farm. And I found from the Renewable Planning Database, it has 24 turbines, each of 2 megawatts. So now that I've chosen my wind farm, I need to manipulate the wind speed data from the Met Office. So firstly, I scaled it from anemometer height to hub heights. Then I converted from wind speed to wind power using a power curve. And then I used a Markov chain method to determine how much of the total power output gets curtailed. And I'm actually not going to talk about any of these methods in any more detail here, just for the sake of finishing on time, and also because in the accompanying conference paper, I discuss these in quite a lot of detail. So if you are interested, then check out this paper when it becomes available, where I describe my methods in much more detail there. So now that I've got the output from my wind farm, I need to optimize the scheduling of my storage. So I did this using Python's package Pyomo, where I used this optimization function here to maximize the profits of my wind site with the energy storage. So I'm just going to talk you through these different terms here. So the first term maximizes the profits from selling power. So that can be power direct from the wind farm or discharged from the battery. The second term minimizes the losses from importing power. So that could be power going to the energy storage. The third term maximizes the profits from selling hydrogen that's generated with the electrolyzer. And the final term minimizes the losses from using curtailed wind. And there are a load of constraints on the storage as well, but I won't bore you with all of the maths here. So just to show you what some of this looks like with the optimized scheduling of the storage, I'm just showing over a small time period here to kind of show you the behavior of the storage at different times. So to talk you through this graph now, because I'm aware it does look a little bit complicated, the red line is the total wind power generation. So the total power output of my wind farm. These white areas represent times when that wind is being curtailed, and the different patterns represent it being used for the different types of storage under my optimization function. So these hashed areas show times when it's being used for the electrolyzer, and these spotty areas show times when it's being used for the battery. And the areas where it's unpatterned are times when it's actually not being used at all and it's being wasted. And that's because in this particular run through, I've undersized the storage. And these blue areas are times when power is being exported. So most of the time that's power generated from the wind farm. However, you can see in the middle of these sections, or hopefully you can see in the middle section, some of that is also power that's being discharged from the battery. And finally, these green areas show times when the wind is being self-consumed for the storage. So primarily for the electrolyzer, but also a little bit for the battery. So we can infer a couple of things from this. Firstly, actually at no point is power being imported. And that's because the import tariff is really high, and it turned out actually it's too expensive to import power for the storage and far better to self-consume the power from the wind farm. Secondly, there's a high level of self-consumption for the electrolyzer, and that's due to the fact that the trade-off between selling the wind directly versus using it to generate hydrogen and selling that favors the production of hydrogen under this particular scenario, my optimization model. We can also see that the storage is not quite big enough to use all of the curtailed wind. So there are some times when some of the curtailed wind is still being wasted. And finally, the discharge of the battery occurs at certain times. And these relate to times when the export price is highest. So you can see around 66 hours and 88 hours in this example. So we then repeated this optimization procedure over a load of different scenarios where I varied the size of the electrolyzer, the size of the battery, the PPA, which is the price that you get for exporting power, and the hydrogen price. So I ran my optimization model over 1 month and calculated the improvement in monthly profits in the case where the wind farm has storage versus the case when there's no storage. And I've included the cost of replacing the storage, which is due to calendar aging. So that's why we're seeing losses in some of these scenarios. So just to talk you through, the green lines represent times when investing in storage shows an improvement in profits at the wind farm, and the purple lines show cases when actually investing in the storage is not economical for the wind farm. So what we can see is that the most economical scenarios are when we've got a large electrolyzer, actually when we've got a small, even zero-sized battery, when the export price is low and hydrogen price is high, which kind of makes sense because for a low export price and a high hydrogen price, it makes sense that we'd generate greater profits through investing in the storage. So just to reiterate, investing in a large electrolyzer can improve the profits, particularly when we have a low export price and a high hydrogen price. And the battery, I found, was typically a poor investment due to its high capital costs. And then I went on to look at, with these different sized storage, how much of the curtailed wind can we make use of? So what I'm showing here is for the 3 different sizes of my electrolyzer and battery, what percentage of the curtailed wind are we able to use? So you can see that by increasing the size of the storage, we can use more curtailed wind. And I found that actually increasing the size of the electrolyzer allowed us to use more of it than increasing the size of the battery. However, the optimum storage in terms of using the curtailed wind was to maximize the size of both the battery and the electrolyzer. However, as we've just seen, that's not necessarily the most economical scenario. So just to finish with a bit of discussion of what I'm going to do with this model moving forwards. So what I want to do is actually apply it on a national scale and optimize the location of wind storage systems. So I want to address the question, where would be the best location to install one of these systems in the UK? And also, in order to answer that question, I want to consider the storage and the transport of the hydrogen. And to do that, I want to identify potential users of green hydrogen, so where the demand for hydrogen might be. And that might also influence the best choice of location for one of these systems. For example, if we wanted to set up a type of green hydrogen cluster where we've got the production and the end use all within a very close region. So that's all that I'm going to talk about today. Thank you very much for listening. And if you've got any questions, then please ask away. So I haven't actually considered offshore in my modeling, but you're right, it is something that I could consider. I guess because I am quite interested in transporting the hydrogen from the moment of production to the moment of usage. In that circumstance, onshore is preferable because you don't have to kind of consider transporting it on land. That is a good point. So there is potentially the option of doing that. So yeah, that is a really good point and something that I will consider when I'm looking at this on kind of a larger scale location analysis.
So University of Oxford and UK, we talk about performance of fully scalable, flexible, transparent, conductive films made from carbon. For the complicated tile. That's to the right. Oh, okay. So I want to start off by motivating why do we even need new materials for transparent electrodes. And there's 2 main reasons for that. The first one being that the next generation or the modern optoelectronic device, they have an ever-expanding list of requirements that they require from their transparent electrode materials. So it needs to be lightweight, flexible, of course, cheap ideally, and scalable, all on top of being transparent and conductive. materials such as especially ITO. We can't keep track with that. And the second reason is that there is a price performance trade-off in these materials as well. So we can make, if you look at the right-hand side, we can make good ITO films on flexible substrates, but they become very expensive if they need to be at a high performance. So the material I'll be talking about today, carbon nanotubes, they are abundant because they're just made from carbon, can actually be synthesized from carbon waste. They're resilient and high performance has been demonstrated. The main issue for carbon nanotubes is that it is really hard to process them in a scalable manner. Okay. We talk about performance of transparent electrodes. We normally use a figure of merit, which is the ratio of the electrical DC conductivity to the optical conductivity, typically taken at 550 nanometers, which is the maximum sensitivity of the light. And if we assume we are an about material, then we can use this figure of merit as a fitting parameter in a curve of transmittance versus sheet resistance. So if we look at such a curve to the right-hand side, we see these colored lines as actually performance lines of the figure of merit that are normally material specific. So, or let's say material specific for a certain process. So if we look at the right-hand side, that's the best published carbon nanotube EVA and transparent electrodes will be quite far off from the other materials such as PSS, silver nanowires, or ITO. And then if we look at the shaded areas, these indicate different applications. So we can clearly see that different applications need different levels of the figure of merit, starting low with an anti-static to a touch panel, screens, OLEDs, and then finally photovoltaics, which is the highest one. So our approach is going to be use this carbon nanotube EVA process, which is already scalable, and try and improve the performance. Okay, so I'm going to introduce the materials quickly, talk about the preparation process and what we learned from optimizing it, and then show you some applications. So I hope everyone has heard of carbon nanotubes before. They consist of sp2 hybridized graphitic carbon. So they have 3 neighboring carbon atoms, 3 bonds, and then 1 delocalized electron in a pi orbital. That means we have really good transport properties along one carbon nanotube. And carbon nanotubes can be classified by 2 chiral indices, which basically state how many base lattice vectors you need to add up to form the circumference of the tube. And they typically have sizes of 1 nanometer in diameter and a few micron in length. Okay, if we now think about applications of carbon nanotubes, we always talk about networks of carbon nanotubes, hardly ever about individual carbon nanotubes. So we need to consider these network properties as well. And if we want to use them as electrodes, the DC conductivity is what matters most. And this is normally dominated by intertube junctions, because as I said, the transport along one tube is very efficient, but once you get transport between tubes, that's where you get the resistance. The problem now is why it's so hard to process them, that because of their high surface area, they tend to have very strong attractive van der Waals forces between them that just force them to agglomerate to large bundles. And then if you look at the top picture again, imagine they all clump up into one. There's no transfer. You lose all your nice nano properties straight away. So the solution we use for that is we use a non-covalent functionalization. That means we don't actually have bonds between the polymer and the nanotube. And we wrap the polymer around the nanotube. And that has 2 benefits. It makes the nanotubes processable in solution, which is a lot easier to scale up. And it also leaves the electronic properties of the tubes unaffected because it does not actually bond to the nanotube. So considering that, we expect a higher transparent conductive film performance for longer tubes because we need less junctions, for more individualized nanotubes, for high nanotube purity, and for lower junction resistances. Okay, now let's briefly talk about the polymer. Ethylene vinyl acetate is a copolymer. Some of you might know it because it is the standard encapsulant for silicon solar cells. It is also extremely cheap, costs less than £1 per kilogram. It's optically transparent, which is handy if we want to make transparent films, and it's durable and flexible. And because it is a copolymer, it means it has two monomers, as shown on the right-hand side. We can actually tune the properties of the polymer by tuning the monomer ratio and also by controlling the chain length. And for this polymer, it has been demonstrated that we can wrap individual nanotubes with a single layer of the polymer if we get the processing right. So that's what we're trying to do. So the preparation process, we start in top lab, so right here. We mix the materials together, so we combine the polymer and the nanotubes in a solvent and apply a dispersion technique, normally used to be tip sonication. Therefore, we break up the nanotube bundles and we wrap the polymer around the tubes. We then separate the remaining bundles that are a lot heavier than the individual nanotubes via centrifugation. Now we need to get rid of all the excess polymer because the polymer is insulating. So we use a different solvent that causes the nanotubes to reaggregate, but keeps the polymer in solution. And again, separate the nanotubes from the excess polymer in a simple centrifugation step. We then use a third solvent, chloroform, which is a really good solvent for carbon nanotubes and has a low boiling point. We apply a quick redispersion step to make sure we break up all the nanotube bundles, and we can then deposit the nanotube EVA dispersion via spray coating on arbitrary substrates at 100 degrees Celsius. Okay. To make this process fully scalable, the only thing that's really needed to change is the tip sonication, because it's limited to volumes of about 10 mil to be efficient, which is clearly not what if you want to upscale it. So we moved away from tip sonication to shear force mixing, which is easily upscalable to thousands of liters and is used in a lot of industry process already. And it's also been shown that shear force mixing is less disruptive to the nanotube, so we end up with roughly 3 times higher average tube length in the films. So with that, the process is completely scalable. And we actually get a second benefit from the shear force mixing, which is that we can use a 10 times higher batch volume already in the lab. And that means we have a much easier time in optimizing our preparation process, because we can compare the outcome of the samples from the same batch instead of comparing batch to batch variations. And that really helped in optimizing this process that I showed in the last slide. So I'm going to show you some results of why the optimized samples are better than they used to be. I think that's much more interesting than talking about what we did different in the process. Okay, so here's some electron microscopy data on the left-hand side before, and on the right-hand side after optimization. And we can clearly see the difference in these honey-like softer areas of the film, which are the polymer. We have a lot less polymer in the right-hand side picture. Again, the polymer is insulating, so that certainly helps in getting a better charge transport. And we can also see that we have a closer nanotube packing, and we have smaller nanotube bundles. If we now do some Raman spectroscopy, we have 3 typical carbon nanotube modes or vibrations. The first 2 are shown on the left-hand side. There's one which is called the disorder mode at roughly 350 inverse centimeters. And then we have a graphitic mode at 1600. And we can take the ratio of the peak intensities of these 2, and we can use that ratio as an indication of the defect density of the nanotubes in the film. And if we do that, we see that we go from a value of roughly 130 for the raw material to 123 for the shear force mix film, and then all the way down to 80 for the tip headed film. So we can demonstrate here that shear force mixing is a lot less damaging to the nanotubes in the film. On the right-hand side, we see the third mode that's typical for carbon nanotubes, which is the radial breathing mode, and that is, as the name says, a radial breathing mode of the entire tube. That is, its position is dependent on the diameter of the tube, so we can actually see which diameters of tubes are present in the sample. And if we then process the nanotubes with different types of EVA polymers, again with different monomer ratios, different chain lengths, we can see that none of that really affects the selectivity of the rapid process, and all different polymers wrap all of the nanotubes present in the sample. And we also found that the type of polymer used does not affect the conductivity of the film. So we can tune the polymer to our needs, and it does not change the nanotube part of the film. Okay, so the third technique I want to show you is small angle neutron scattering. It has the benefit that it's not just taking a small part of the film and images that, it's more an averaged representation of the internal structure of the bulk sample. So we see scattering data on the left. It's a bit not so straightforward to understand, but we can just fit it with a power law. And then we are mainly interested in the exponent P, which is called the Perot exponent. And higher values of that exponent indicate that we have denser packing in the sample. And if we now compare these different samples that are processed in a different manner, we can find that this exponent actually correlates with the transparent conductive film figure of merit. So we get the higher film performance for a higher packing density, which is also what we saw in the SEM images before. And that confirms that the main outcome of the improved processing is actually that we have a closer packing density between the nanotubes, which decreases the junction resistance. Okay, and I want to show you some applications of these transparent conductive films. So on the right-hand side is just a picture taken through one of the films. You can see they're quite transparent and don't really affect the color scheme too much. On the very right-hand side, there's a stripe where there is no film disc. So there's really not that much difference. So one thing we were interested in is how do these flexible films perform under bending and folding? Because if they don't do well, then there's no point making them flexible at all. So what we did is we did steps of 100 bending and folding cycles. The main difference between these two, as you can see on the left, is the bending radius. So folding has a much smaller bending radius than the bending. And then we measure the sheet resistance locally at that point of highest stress after every 100 steps, and then just compare that for up to 2000 cycles. And we find that in all of the samples, the change in sheet resistance is relatively small, only a few percent. And we can actually fit this data really well with a logistic curve that allows us to assign an upper bound for, well, assuming an infinite number of folding cycles to the sheet resistance, which is below 2 times the initial value for all of the samples that we have measured. And what we can also do is we can compare samples that are made with different polymers. So again, we can tune the polymer to our needs. And we find that polymers with a higher vinyl acetate ratio and longer polymer chains perform better than polymers with shorter chains or less vinyl acetate in this application. Okay, now if we want to make some sort of real life application from these transparent conductive films, we can start with an easier one, which is a capacitive touch sensor. So as a proof of principle, we made a 4x4 pixel matrix. It's not very high resolution, but it worked. And so what you do is you basically just connect each row and each column to a microprocessor, and then you send short current pulses to your device, and then you can measure the time constant of how this voltage is decaying after the pulse. And by doing that, we actually found that we get a linear relationship between the signal to noise ratio of that signal that we get for the touch sensing and the sheet resistance. So this again confirms that there is a threshold of conductivity that we need to get a working capacitive touch device from these transparent conductive films. And finally, because we are, at least in my CDT, working towards making better solar cells, we put our films in a perovskite solar cell device where the stack is shown in the middle. So we have FARP as the active material, and then we put our nanotube EVA film in the whole transport layer to replace the lithium TFSI dopant that is known to cause stability issues when it's there to dope the spiral or metal layer. So replace that dopant to make sure we have a high enough electrical conductivity in the whole transport layer. And what that allows us to do is we can actually decouple the energetic requirement and the transport requirement, the whole transport layer. And we find that this actually works really well. So we're still working on that to get high efficiencies, but you can see that in this batch, for example, the nanotube devices actually outperform the control device, which is the what Spiro is not so standard anymore, but it used to be standard whole transport layer. So it works really well. If we look at the right-hand side to our champion device, yeah, there's still some shunting because the nanotubes, of course, are really long and sticky, so they tend to stick through your layers. But we're working on several approaches to tackle that problem at the moment, and hopefully get the efficiency a bit higher. But the best device we have so far is at 16.3% stabilized maximum power efficiency, which is the highest value for any solar cell incorporating nanotube EVA layers. So with that, I'd like to close. Yeah, we've demonstrated by optimizing the preparation process, we can make these films fully scalable. We can tune the EVA polymer to our needs. We have a very versatile deposition. We can also just spray coat on paper, for example. It doesn't really affect the sheet resistance of our films at all. We can make high uniformity films, which is quite hard for carbon nanotubes, down to about 20 nanometer thickness or 95% transmittance. And we have improved the performance in the figure of merit by a factor of 100. So we moved all the way from this position here, right on top of P.PSS. Yeah, and we can demonstrate some nice applications as well. So with that, I'd like to thank you for your attention and my collaborators for all their help and my master's students for their help. Thank you.
Do you have any questions?
A really interesting talk. Have you tried making your perovskite solar cells without the Spiro, just with the carbon on top? Because you can make them with carbon paste and things, replacing the
Yes.
polymer.
So we have not tried specifically. Graphite paste or carbon black or whatever. Yep. Just because the energy levels of the carbon nanotubes do not align as well with the perovskite. And there's another point to that, because EVA is non-selective in the wrapping process. We actually get a whole range of energy levels.
That's good. Really quickly, other question. You talked about scale up and you said one of your main issues was your tip sonication.
Yeah.
to me, one of the main issues is the solvents that you're using, which are completely non-scalable. So do you have any ideas about how to scale those up, maybe?
So I didn't touch on that. I know industry really doesn't like chloroform, for example, or well, any of the solvents we use really. Yeah, so there's certain ways you can recycle the solvent so you can lower the consumption. But we actually have spent quite some time trying to replace these solvents. But it really doesn't work. So yeah, we're working on that. The process itself is scalable, the solvents maybe not so much, yeah, likely.
Hopefully a quick question. How do the junctions actually form between the nanotubes if they're wrapped up in these polymers?
So it's hopping or tunneling transport. So let's see. Yeah, the charges basically jump between or tunnel through the potential barrier between tubes. And yeah, if there is much polymer wrapped around the tubes, then that's why we get such a higher sheet resistance. So I think it's a process that is really strongly dependent on the distance that you need to cross. So if we have less polymer, then we get a lot better conductivity. Yeah.
Oh, sorry.
It was just about carbon nanotubes diameter. So you said that they were fixed in the ramen. Would different different groups and have different diameter carbon nanotubes, and does that change like the properties of what you can use the nanotubes for?
Sorry, what do you mean different groups? Different groups of
So,
carbon nanotubes?
does everyone have the same diameter for their carbon nanotubes, or can you get variety of diameters for your carbon nanotubes?
No, not everyone has the same diameter. So there's a whole range of nanotubes. You can go all the way from below 0.5 nanometers, which has, I think, around 1.5 EV band gap, all the way down to, well, you can make them as large. No, not everyone has the same ones. Now been a bit more controversial because for the junctions, if you have a larger diameter, you get a larger cross section in the junction, and that makes the crossing the junction more effective. So that's yeah,
you change that distribution of lengths, right?
Ah, yeah.
Because you optimize your force mixing to increase it even more. So you don't really have that.
Yeah. So the thing is, you need a certain force to break up the bundles, and that, in terms of shear force mixing, translates to a certain running speed, rounds per minute. Wrapping it all. Then if you're too high, of course, you just introduce more defects. But there doesn't really seem to be a sweet spot in between the two where you only get wrapping.
Yeah, hi, so here's my real title. So it's xanthan gum as a water-based binder for P3 sodium nickel manganese oxide. It's a cathode material used in sodium-ion batteries. So start off with a bit of background. Let me. Okay. So sodium ion batteries essentially work in a similar way to lithium ion, which you find in your phones and laptops. So what happens during charge and discharge is that you have your alkali ion shifting between the cathode and the anode. So this occurs in the same way in sodium ion batteries. So the added advantage of that is that you can easily transfer sodium ion technology into lithium ion systems because they essentially work the same way. And also sodium is much more abundant compared to lithium. So it's a more sustainable, cheaper alternative in that sense. And so electrodes are generally composed of your active material, carbon, and a binder. So they all have their roles. So obviously the active material is the thing that gives you your energy, your capacity. And then the carbon is in there to improve electric conductivity. And then you have the binder, which essentially keeps everything all together and stuck onto the current collector. It has several roles as well. So it has to make sure it doesn't really affect electronic and ionic conductivity. And also it's just to make sure everything continues to stay together as the battery is cycling over a number of times. So generally how these electrodes are made is that you mix all your powders together and you put a solvent in, and then you cast this slurry onto your current collector. So at least in this situation for cathodes, we use aluminium foil. So traditionally in lithium ion and sodium ion batteries, we use a PVDF binder. I'm not going to pronounce that. So generally the advantages is that it's thermal and chemically stable, and it has really good adhesion, so really good for a binder to be sticky. But the cons is that it has weak mechanical strength. So some battery materials, especially like silicon, undergo really large structural changes during cycling. And PVDF isn't really mechanically stable. So what you end up over a number of cycles is that you get chunks of areas sort of breaking off and they become electrically insulated. So it doesn't really add to your capacity in the battery. So which isn't really good. And another really bit negative thing about PVDF is that it needs an NMP solvent to dissolve it when you are making the slurry. And NMP is really expensive, it's harmful to the environment and harmful to your health. And so really careful handling is needed of this solvent. However, there are some alternatives, and one that I've been looking into is xanthan gum. It's easily available. You can go buy it from Tesco's. So it's cheap and it's non-toxic and it's water soluble. So we don't need to use this NMP solvent. And it's found to have really good adhesion. So it keeps all the components in the electrode together. And it said because of the functional groups, the hydroxyl and carboxyl groups, it can, so that's what helps to keep the good adhesion together. And also because of the type of bonding and its general structure, it can potentially accommodate a volume change better than PVDF. And it's also been found to be really stable in electrolyte and a wide voltage range. So although one thing to point out, because it's water soluble, some sodium ion cathode materials aren't really water stable. They end up taking water in the sodium layers, as you can see in this diagram. So we have a sodium layer there. And when it's exposed to water or like the ambient atmosphere, it takes up water and you end up forming this hydrated phase. And it basically has a really negative impact on performance. So it basically blocks conduction pathways for the sodium. And also because you get expansion of this structure in the C-axis, you can sometimes see like cracks and areas again get isolated from the rest of the material. However, so different things can affect water stability. And one thing is the different elements that you put into your cathode material. So we could see that the structure here on the, keep forgetting. So that's your, on the left-hand side. So this structure is sodium, nickel, manganese. After immersion in water, there are no additional phases formed. So it's really stable in water. But then you can see these additional peaks form after immersion. And this is with the addition of cobalt and iron. So that negatively impacts the water stability. So they might not necessarily be a good candidate for using water-based binders. But the structure I'm looking at, I found that it is relatively stable in water. So here on the left-hand side, I have XRD patterns of the pristine material versus when I just stored it in a desiccator for a few months and it showed no change. And then I went rummaging through my cupboards and found an old sample, and it was 4 months old. And I did find some additional hydrated peaks. But then I found this is really reversible, and after drying in a vacuum oven, they disappeared. And then I decided, why not just throw it in some water, see what happens. And in a regular drying oven, afterwards I did find a really small amount of hydrated phase formed there. But then again, after drying in a vacuum oven, that went away. So it's a really good candidate for water-based binders. I did some SEM imaging just to see if there's actually any difference on the morphology of the material, and I didn't find any significant difference. So you can see that I do have quite small particles, like in the range between 100 to 200 nanometers. But after being immersed in water, I couldn't really see anything. And then there are some more SEM images of the prepared cathodes, and I have secondary electron images and backscattered. So you can see a different contrast in these backscattered images. There are regions of more lightly colored areas, and that's my active material. So you can see I've got quite significant agglomeration in both of them. So it's not, these aren't forming because of the cathode preparation, but because of how I synthesize my material and the fact that they are fairly nanosized. So it was explained in the previous talk as well. Smaller particles tend to agglomerate. So this is something I'm going to look into the future, how to sort of prevent this agglomeration, whether that be while making the slurry or just after I have synthesized my material, so possibly ball milling or sonication. So that's something I'll look at in the future. Then I looked at the electrochemical data and I found no difference in performance with the different binders. So you can clearly see that exposing the material to water has no significant impact on the performance, which is good. So I'm able to use a more environmentally friendly binder, at least for this material, and have no negative impact. So potentially with better mixing, there might be some improvement, because in the literature, people have seen better performance compared to when they use PVDF binder. How are we doing for time? 3 minutes. Okay, I'll skip this bit because it's just an additional bit. So, no, actually I do have time. So then I did some CV data just to see if there's any difference in redox activity. And again, I couldn't really find any significant difference. This is more like how my material is performing. It's not as widely investigated. I need to find out what exactly occurs during cycling of these materials. So at high voltages, you can see this redox peaks really quickly goes down in intensity, and that's probably the main cause of my capacity fade. So I need to figure out what that is due from. So I've read that it could be oxygen redox. So I could get oxygen gas coming off my material and hence loss of active material. And that's why I see rapid decline in capacity, but I need to get that confirmed. But there's also other things that happen in the material and these voltage ranges that I need to figure out. But all in all, there's not much difference between the two when using the different binders. So see that xanthan gum is, again, stable in these different voltage ranges. And then again, I looked at different cycling rates, and when I use both of the binders, they both perform perfectly fine and similar to each other. So in conclusion, so the structure I'm researching is P3 sodium nickel manganese oxide. It's fairly stable in moisture and is easily reversible back to the pristine material. And there's no negative impact on the electrochemical performance. So we're able to use more sustainable binder here. So yeah, and in the future, I need to figure out why the capacity is fading so quickly in certain voltage ranges. So whether it is this oxygen redox or there's more severe structural changes going on. So that's the end of my talk. I want to thank my supervisors in the group and the organizations that have funded this project. So yeah, any questions?
That's like using your cells.
It's 1 molar Na+6. Yeah. So at least whether XRD is the cathode is dried before putting into the cell in a vacuum for a few days.
It might be worth looking at like sort of posts.
Yeah. Hi.
I just have quite a naive question because I'm not terribly familiar with your system, but you showed the cyclic photometry for the xanthan gum, and you're very clear, you had your oxidation peak that was decreasing with cycles. I don't know if you can go back there. Oh.
There you go.
Yeah, so you have your very clear oxidation peak, which is then decreasing as you continue cycling.
Yeah.
And then is that reduction peak at about kind of 4? Is
Yeah,
that
it's like
connected
about
with that
4.2.
oxidation? So do you have like, are they connected with
Yeah,
each other?
these two
So
are
you
connected here. Yeah.
Okay.
I mean, I'm not sure why I have this doublet here. It could be something with my processing because I don't see it in other.
It's kind of interesting. I was going to ask about that.
Yeah.
That was. Okay. They're connected in which case it's probably not oxygen. Well, water oxidation, is it?
So here I think it might be oxygen redox. So here we have it. Gosh. Oxidation and then redox at the bottom. So there's sort of like polarization. So sometimes it's not really reversible, or there's like resistance in the material. So that's why they're not exactly mirrored. If that's your question.
Kind of.
Yeah.
Okay.
Questions? No, I've got one question then quickly, if that's okay. What was your selection criteria for xanthan gum, and what other choices did you have aside from xanthan gum?
Yeah. So but this was just like some experiment I had in my free time. I was just basically looking at papers. There was another one that did it on a similar stoichiometry to mine, but a different structure. And they tested xanthan gum, sodium alginate, and guar gum. So again, another types of similar polymers, and they found xanthan gum was the best. So that's why I started off with that one, because the materials are quite similar. Yeah.
Oh, thank you.
Break for coffee and then come back at 3:30.